The last part of chapter 3 deals with periodic properties or periodic laws, periodic trends. We already looked at atomic radius and density, right? We looked at the boron group and decided that density increases within a group and radius increases within the group, and that was pretty easily explainable. Now, to bring that back, if density is the mass over volume ratio, right? And we have an increase in mass within the group, right? We have more and more protons and neutrons, so there's an increase in mass. But we also have an increase in the number of electrons, and that increases. So mass increases and volume increases. If both of those increase proportionally, then we don't have a net change in density. But we do see a periodic trend where we have an increase in density. It cannot just solely be attributed to the increase in molar mass. You have to look at the ratio. So what happens with volume, it actually decreases relatively to the increase in mass. Overall, there is an increase in volume, but, and I'll tell you why that is. Okay, if you look at the simple shell model, let's say we have boron. Boron has 5 protons in the center. Okay, and so the first 2 electrons go on the first shell, and then we have three more to spare. And so you've got this 5 plus charge that pulls on these electrons, that holds them in, and so they don't fly off, right? And so we have a third one that goes here, and so that pulls on it, and a fourth one, and a fifth one. And see, you are adding these electrons on the same quantum level. Therefore, the effective nuclear charge increases, and that's because as we add electrons, we also are increasing the atomic mass, the charge in the center, right? So if we now go one over to nitrogen, what happens is you add, and I'm not going to put it there because I want to focus on boron for now, but if you put another electron here, the only electrons that are shielding are the ones that are lower here. See, these don't effectively shield each other, so this gets pulled in tighter and tighter. So the effective nuclear charge increases within the group, which decreases the volume relatively to the mass increase, right? If that makes any sense, right? Because you're just simply increasing the number of electrons here. So now if I go down from boron to aluminum, which has 13 plus in the center, okay, so we have 2 electrons on the first quantum level, and then 8 on the second. 1, 2, 3, 4, 5, 6, 7, 8. And then we have, so the volume definitely does increase, right? But your effective nuclear charge also increases. Okay, it's going to pull with the plus 13. It can pull this in tighter, right? So the shielding is not very effective. Your effective nuclear charge increases, shielding decreases, and your volume. So what you have is you have an increase in mass and an increase in volume, but the increase in volume is not as large, therefore decreasing the ratio of mass over volume, and that's how you get an increase in density. Now the radius one is much easier to comprehend because you're just adding shells. You can see that just the way I've drawn it. The more electrons you have, the further out you go. So within a group, the atomic radius increases, which is reflected here. And if you remember, we brought this up because Mendeleev actually predicted the increase in, or the density, and he had predicted the properties of gallium, the electronic properties, the binding properties, ratio properties, as well as radius and density. And so he knew very well that trend would have to be between 7.3 and 2.7, that of aluminum and indium, the density, and the radius as well. And so that was well done. Okay, so now we're going to look at all these periodic trends. I mentioned a couple already. I mentioned atomic radius, I mentioned density, and I mentioned effective nuclear charge, right? So effective nuclear charge is how strong the nucleus can pull on the valence electrons, on the outer electrons, right? Atomic radius is the size of the atom. Ionization energy or ionization enthalpy is the energy required to remove an electron from its outer shell. And so then a lot of these are related, right? If your effective nuclear charge is high, then your radius is going to be smaller and your ionization energy is going to be higher, right? If effective nuclear charge is high, so if effective nuclear charge increases within a period, then your atomic radius has to decrease within a period and ionization energy has to increase. See, they're all connected, and I will talk about all these in great detail. So you can memorize the trends so that you can list them in increasing order or decreasing order of a particular trend. But it's also good to understand it. This way you don't necessarily forget down the road if you happen to take quantitative analysis or inorganic chemistry, or whatever you're taking, or biochemistry for that matter. Electron affinity is the energy released when you add an electron, right? So if you remove an electron, metals have the tendency to remove electrons, and nonmetals have gain electrons. So there's energy released, there's a trend, and then electronegativity, which is really important. It correlates to bonding and how things bond and whether we have polar or non-polar bonds. So that's the ability of an element to draw electron density towards it. And I'll explain all that. As I said, density, we know mass over volume ratio and metallic character. And we can guess some of these based on what we know about the periodic table already. Okay, let's get back to effective nuclear charge, right? So we have an actual charge in the center, which is what I was trying to tell you for boron. Boron has 5 protons in the center. That's its actual charge. But in between the electrons or the outer electrons and the nucleus there's some shielding here. Okay, so there's a shielding factor, right? So effective nuclear charge is actually Z. This should probably be a minus, right? So you're subtracting the shielding factor here, and there's a formula you can use. We're not going to use it, but you can actually calculate effective nuclear charge. And so what happens if you look at an atom, effective nuclear charge, as you go down in a group, it actually decreases. Okay, so the further you get away, the weaker the effective nuclear charge, right? So if you have, even if you just have +2 and +2 electrons, you are directly able to pull on that electron that's on the first shell. And the further away you get, the more and more you have shielding. Okay, so within a group, effective nuclear charge is weakened. It gets weaker. Okay, but within a period, effective nuclear charge increases. Okay. And so let's just take a look at the third period. Okay, so if you have the periodic table, this is going from sodium to magnesium to aluminum to silicon to phosphorus to sulfur to chlorine and to argon. So that is the third period. If you have a periodic table, you should look at that, right? And so this is 11, 12, 13, 14, 15, 16, 17, and 18 is the atomic number, right? So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. That's the first shell, and then we have 11, 12, 13, 14, right? So for sodium, we have a charge of 11, and we have 1 electron. Okay? So it has some ability to pull on that. Now, if we add a proton here, if we go to magnesium, you add a proton, so you increase the charge in the center, and you're adding a second electron, but it's next to this electron. These 2 electrons, they don't shield each other. So the charge, so this gets actually pulled in. So effective nuclear charge increases within the period, right? You take that one further to aluminum, you get an increase of 13. So you're increasing the charge in the center. Again, you're just putting an electron on the outside. So you are going to increase effective nuclear charge, and that happens all the way. See, you're adding up to 8 electrons on this shell all the way to argon, and so that's just going to decrease the effective the radius as well as increase the effective nuclear charge, right? So increasing charge in the center and the pull, because they don't shield each other. But once you pop out to the next element, potassium, you adding to the next shell, you see an increase in radius there, but you still are going to see a decrease in effective nuclear charge. Okay, so effective nuclear charge is you have a decrease within the period of you have a decrease within a group, right? So the further away you get from the nucleus, the weaker the pull, and within the period you have an increase in effective nuclear charge, which is directly related to the atomic radius, right? So the atomic radius decreases as effective nuclear charge increases. So atomic radius actually decreases within a period. So lithium is larger than beryllium. Beryllium is larger than boron, and the smallest one is neon, because effective nuclear charge just pulls everything in. So you see a decrease within a period, but an increase within a group. Okay? So that's what we have here. And so covalent radius and atomic radius are similar. The covalent radius is the distance between the two nuclei of an atom in a chemical bond. So that's when that's just a bonding. But so let's just take a look at different kinds of radii. So atomic radius is there's no bonding, right? You just have, if you have boron, you have 5 electrons, and there's no overlap here. Covalent radius, there is some overlap. Okay, so covalent radius is half the distance between centers of adjoined atoms. So the trends are the same here. And so this is what we want to look at. Atomic radius. You see this here nicely, what I was telling you, how sodium to argon in the third period, that there's a decrease in atomic radius because of that increase in effective nuclear charge. And you have the trend going within a group here, and you see this for every single group. Carbon, there's an increase here all the way to lead. You have an increase in atomic radius within a group. Okay, and so this is again atomic radius. You can see these trends here, right? So here you have an increase within a group: lithium, sodium, potassium, rubidium. You see that increase. It levels out a little bit, but you have that really sharp decrease here, going from lithium to neon and sodium to argon within a period. And then of course you fill up that noble gas, and the minute you stick another electron on there, it goes on the next quantum level. You see a huge increase in atomic radius here, all right, because you're going up to the next quantum level. Now there's some interesting little discrepancies here when you hit the D's. Okay, and so what happens here is it goes down and then it goes back up, and so there's actually a lot to be said here, but I just want you to focus on the regular trends. And then another thing that's pretty interesting is here that from the 4D to the 5D here, right? So those are the 4D elements, and here are these are the 5D, and these are the 4D elements here. And so what happens is they almost have the same radius, and that's because it's all related to that effective nuclear charge. See, you have these F elements, if you remember, after lanthanum, you get 14 elements from the F block that are inserted. So you've got 14 elements. So you have 14 electrons that are added on the same shell. So you are actually really pulling that in. It's a contraction. This is called the lanthanide contraction, because element 58 through 71, those are the lanthanides. And so you have these 14. They decrease that radius so that the 4D elements and 5D elements are almost identical in atomic radius. So something like ruthenium and osmium, which is under iron, ruthenium and osmium have almost the same atomic radius. What about ionic radius? Okay, so we haven't really talked about ionic and covalent bonding in any great detail. But what happens here is if you look at the electronic configuration of sodium, right, that we just did in the last lecture, 4s2, 2p6, 3s1. This is the valence electron. It's in the outermost shell, okay? And what I haven't told you yet is that, because bonding is in chapter 5, but it's all about bonding. We don't just deal with elements. Most things we deal with in nature and in the lab and in the factory or whatever, our compounds are when you combine elements together to make covalent and ionic compounds, right? And so the metals have, everything on the periodic table has a tendency to want to be noble gas-like, right? So everything wants to be argon or neon or krypton-like, and that's because they have a full electronic configuration, right? So argon has the configuration helium 2s2 2p6, or 1s2 2s2 2p6. That is the electronic configuration of argon, which is what happens when you remove this electron here, right? So this is kind of an oddball. Sodium has a single electron in the outermost shell. So it is really easy for sodium to remove this electron and become sodium plus. But what happens to the atomic radius, or the ionic radius, because now we have an ion, when you remove an electron, it has a drastic drop, as you can see here. It goes from 0.186 nanometers to 0.098 nanometers. It gets pretty much cut in half. Look how that shrunk, right? And so just look at the electronic shell. There is no more d orbital, 3s orbital. It's gone. It shrinks, right? So you want to be careful. And the same thing happens when for chlorine here, right? So chlorine is still on the same shell, yet when you add one more electron to the p orbital and you fill up that last p orbital here, it has a pretty drastic increase in atomic radius here, right? So that increase is largely just adding that one electron. So all you're doing here is you're taking chlorine and you're adding one electron to make the chloride anion. Okay, so the anion implies a negative charge. And to drive my other point home is everything wants to be noble gas-like, right? So here we have an electronic configuration that is almost that of argon. Is there's one away, and instead of giving up, oh my God, that's a 5. Jesus. Okay, so this is a 5. And so this is a 6. So I'm glad I caught that, because that was just going to be bad. Okay, so really bad. Anyway, it's 8 total. It's 2 from S and 6 from P. So 3s2, 2p6, right? So we really just need one more electron here to make it noble gas-like, which is a lot easier than removing 7 electrons, right? So there's a lot to be said here. But as far as ionic radii is concerned, you want to be careful. So if I ask you to rank the third period of their ions, you're going to have to think about that. There's a clear cut between those that are cationic, that are losing electrons, like this is going to become +1, this is going to be +2, this is going to be +3, and then silicon is either going to be +4 or -4. For argument's sake, we say +4, and then these are going to gain electrons. So you're going to have -3 and -2 and -1. I'll let you think about that and see if you can rank them, but for sure be able to rank and understand and explain atomic radii. All right, I'll have to fix these slides before I update them. But I'm glad I caught that, right? Obviously, the electronic configurations were wrong. Ionization energy is the energy required to remove an electron. And that's exactly what we were just talking about, right? Sodium loses an electron. You can write an equation. You have sodium here in the gas phase with its one valence electron, right? You take that valence electron away. You kick it out. There it is, the one electron. And so there's some energy associated with that, right? And so it makes sense. Do I have a periodic table here? Nope. But it makes sense that, you know, if you're looking within a group, right, we said that effective nuclear charge decreases. So if you go from lithium to sodium to potassium, your effective nuclear charge weakens, right? The more and more shielding you have, the easier it's going to be to remove a single electron from its outer shell. So there is a decrease in ionization energy within a group. What do you think happens within a period, right? It's all connected. Atomic radius increases, therefore it's going to be harder to remove an electron within the period, right? So if you go from sodium to magnesium, it's going to be just a little bit easier to remove that electron from magnesium, and then aluminum, and I mean harder. The effective nuclear charge increases, right? So it's harder and harder. It's going to pull tighter and tighter on that, right? So we have an increase with atomic number in the period, an increase and a decrease within the column here, right? So atomic radius, effective nuclear charge, it's all related to that particular trend, right? And so that's reflected here as we chart the atomic number and then the energy required to remove an electron. So going from lithium within a period, it gets harder and harder as you go up the trend. So you have an increase, and you see that again here. If you look within a group, even within the noble gases, you see that decrease so it's just hanging on to that outer electron less tight within a group, and that's ionization energy. Okay, so these trends are for the first ionization energy, meaning for the first electron that that can be removed, right? So sodium, you would expect only one electron to be removed. Magnesium, you expect two electrons to be removed, but the trend is for the first ionization energy, right? So and you see this also reflected here that you can remove a second electron from magnesium. If you look at the electronic configuration, it's going to be neon and then 3s2, which means if you remove two electrons, you are going to have a noble gas core of neon. And so you expect all of the elements, all of the alkaline earth metals in the second group that all have two valence electrons to lose those two valence electrons to become +2 cations implying they're positively charged. So magnesium will be +2, calcium will be +2, barium +2, strontium +2. They all are losing two valence electrons, and that's why they're in the same period. They have the same electronic configuration. They lose, and that's why they have the same ratios with other elements. Okay, so for magnesium, the energy for the first ionization energy in the second is relatively low, but a third one would remove an electron from a full shell, and that would be humongous here, right? That's why you see that zigzag line. At some point you can't, and so even for something like chlorine, the first ionization energy is not all that bad, but of course it's more likely to gain an electron than it is to remove an electron. Yet you can actually remove an electron even from argon, and but those are of course relatively high. Electron affinity is the opposite of ionization energy, and it's the energy released when you add an electron to its outer shell. So this actually it releases energy here, right? So here we have the electron on this side. We're adding it to the nonmetal. We obtain the chloride anion here with an added electron, and that releases energy. And so the periodic trend here is there's an increase in electron affinity within a period and a decrease down the column. Okay, so it's not quite as easy to see, but you sort of see here the energy released for lithium by adding one electron is less than that of fluorine. Obviously, fluorine wants to have that electron become neon. Like none of those have release any kind of energy because they have a full valence shell here. The decrease within a column is not quite as obvious, but you can sort of see here from to 53, 48, 47. So decrease within the group, increase in energy released within a period. All right, what else we have? Metallic character. It's quite obvious if you remember that we have nonmetals on the right, metals on the left, and that we have this zigzag line that divides them. It makes sense that as you go within a period, you're going to see a decrease, right? You're going from metals, sodium and magnesium as a metal, to going into the nonmetal range. It makes sense that you would see a decrease in metallic character within a period. And then within a group, the same thing here, right? If you pick a group that starts with a nonmetal, like nitrogen here is a nonmetal, phosphorus, nonmetal, metalloid, you go into the metal region, you see an increase in metallic character. But that's also true for group 1 here, right? Where they all are metals except for hydrogen. And so there's a metallic character increase within a group and a decrease within the period, right? So just as shown here. Electronegativity, really important for bonding, but I'm going to bring this back up. It's for the bonding chapter for right now. Electronegativity is the ability of an element to draw electron density towards it, right? Okay, so it's all connected to what I've said already. If you have something like lithium, it is not going to be very electronegative, right? It's going to be the opposite. It's going to be electropositive. And that's because it doesn't want to hang on to its electron density. It has one electron in its valence shell. It wants to get rid of it. It prefers to be lithium plus, sodium plus, potassium plus, and engage in bonding. Lithium is really reactive. Sodium, you may have heard people throwing sodium into toilets and blowing them up, right? Because sodium wants to get rid of that electron, and it will do so at any cost, even if it costs a blown up toilet, right? So it makes sense that the metals, those things that are on the left are not electronegative. It makes sense that the nonmetals are electronegative. Therefore, you see an increase in electronegativity within a period. The closer we get to the nonmetals, the more we see an increase in electronegativity. Okay, and so this is a nice little chart. It's not from the Tro book. It's actually from an Intro to Chemistry book, Adventures in Chemistry, which hasn't been updated in 10 years. But the Tro book has a similar chart where you have these. Fluorine is the most electronegative element on the periodic table. It comes towards you here. It's the highest up, and it makes sense because fluorine is one away from being neon-like, and it's really close to the nucleus, right? Fluorine just has 9 protons here, so you've got 9 protons in the center. You've got 2 valence electrons on the first shell, and then the other 7 are on the second shell. So those 7 electrons are going to feel that effective nuclear charge. They're just 2 electrons shielding that. So it's almost like you have a +7 charge on every single one of those electrons, not just a +1 charge. So not only do we have a high effective nuclear charge and a very small atomic radius, you also have a very high electronegativity because it just wants to have, it can just rip one more electrons away from lithium or sodium or even aluminum and other things. It's not very hard to do for fluorine and to become fluoride. So that's why it's the closest, the most electronegative element on the periodic table. And if you think about it, as you go down within that group, that electronegativity is going to decrease. And that's just simply because you have shielding, right? So once you fill up that second shell, you have now 8 electrons that are shielding that. And yes, you have another 7 electrons on the next shell, and you have an atomic charge of +17 for chlorine. But that shielding just weakens that effect of that nucleus. So you see a drastic drop from 4.0 to 3.0. In fact, if you look at these numbers, there's a fairly drastic drop in electronegativity from the second to the third period. And then not so much anymore here, right? So 1.0 difference, and then going from chlorine to bromine is just a, and that's important too to note, right? And then you got to look at this oddball here. They put it in space. It's not here. It's not over here. It's just they didn't know where to put it. So you would do well remembering that as far as periodic trends as electronegativity, it fits in here between boron and carbon. So that would be a really good thing for you to remember, because that's going to help you later on when we talk about covalent bonding, okay? But for now, electronegativity, know what it is. the ability of an element to draw electron density towards it, and the trend is it increases within a period, it decreases within a group. I have one more thing, but I've talked for 30 minutes, so I'm actually going to make a fourth lecture that should be really short.